Welcome back, protein coders. Let's build some coding muscles. Today we're gonna see DSU or union find. Disjoint sets are the sets which doesn't have anything in common. Okay, that's why they are called disjoint sets. And in disjoint set union, what we do is we combine those sets. Okay, suppose we have two disjoint sets. If we do union, we will combine them and make a bigger set. In DSU, we have two operations, union operation and find operation. In union operation, as I told, we are combining two sets. Suppose union 0, 1, then we will combine 0 and 1. Union 2, 3, we will combine 2 and 3. Okay, if I write suppose union 0 and 2, let's say, then I have 0 and 1 here, and I will combine 2, 3 here with 0. Okay, so this is the union operation, combining the disjoint sets. Okay, similarly we have find operation. In find operation, let's say I say find 1. So that means find the ultimate root parent or the ultimate parent of the 1, which is here is 0 in the final graph which we got after doing union. If I say find 3, then 2 is the parent of 3 and 0 is the parent of 2. So the ultimate parent is 0. Find 6. 6 is still independent, so 6 is the parent of itself. Okay, find 2, again we will get 0. So this is the overview of this union and find. Let's see, we have a parent vector here to mark the parent while combining. Okay, so let's say 0, 1, then let's say 0 is the parent of 1. 2, 3, union 2, 3, then 2 will become the parent of 3. If I combine 1, 2, so 1 will become the parent of 2. Similarly, if I combine 5, 6, then 5 will become the parent of 6. And here I'm doing union just based on my preference. There is no rule like if I am combining 5 and 6, then 5 will become parent or 6 will become parent. It's just random. Okay. Similarly, find operations. Okay. Now let's see find in much more detail. Find is the function to find the root parent. Okay. So let's say I have to find the parent of 3, then the 3's parent is 2, 2's parent is 1, 1's parent is 0. Okay, let's have our parent vector here. Now let's see in the vector carefully. I am doing find operation of 3. So 3's parent is 2, 2's parent is 1, and 1's parent is 0, and 0's parent is 0. That means when we get a node which is equal to its parent, that means that is the ultimate parent. So let's write down our find function. We will use recursion here. So let's say int find takes an argument as int x. If parent of x is equals to x, that means we got the ultimate parent, we will return x. Else what we will do, we will call this find function again for the parent of x, and at the end of the recursion, when we will find a situation where parent of x is equals to x, we will return. Okay, so this is all our find function is. Now let's write a simple DSU class, then you will understand better. Let's have our class DSU. Okay, and what will have a vector of integer parent. Let's define a constructor in which we'll take the size or the number of nodes, parents.tree size n, and we will initialize every node to be the parent of itself first. Okay, in our constructor. Now let's write our find function. Int find, int x as argument. If parent of x is equals to x, that means we find our ultimate parent, we will return x. Or else what we'll do, we will call recursively return find of parent of x. So that's our find function. Now let's write our union function or unite function. Let's say void unite. And we'll take two nodes, int x, int y. First thing first, we will check for their ultimate parent. So let's get their parents. Int px equals to find of x, int py equals to find of y. And if px is not equals to py, then only we will merge them. And it's not simple, you can write parent of px equals to py also. Let's see once again what we have done. We have defined a constructor to initialize the parent vector, then we wrote our find function, right? Parent of x equals to x, then means we got the ultimate parent, will return x, else we will call recursively. Then in the union part, we are just getting the ultimate parents and checking if they are not equal, then we are merging them. And it's a random choice. You can write parent of px equals to py also. Okay. Now let's see the first optimization for find. Let's say we have this graph after doing the union. So if you do find of 3, we have to do 3 calls, right? Like 3 will go to 2, 2 will go to 1, 1 will go to 0. Similarly, if I do find 2, I have to make 2 calls in the recursion stack, right? From 2 to 1, then 1 to 0. And for the same path, so what is the issue here is we are doing repetitive work here. Okay. That's why a concept called path compression comes into the picture. Let's see how path compression gonna help us. So if we again do find of 3, then what we'll do, we will again go from 3 to 0, but while returning, we will mark the parent of 1 as 0. We will mark every node with the root parent, okay? Then from 1 to 2, when we come back, we will mark parent of 2 as 0. Similarly, when we come back from 2 to 3, we will mark parent of 3 as 0. In the code of find operation, there will just a slight change. We will mark parent of x equals to find of parent of x, that while coming back, we are marking the parent node of each node with the ultimate parent, okay? Now let's see one another problem. If I do the following union operations without having any constraint or rule, okay, I can end up having a very skewed tree. You can see in this example, union 0, 1, union 1, 2, okay? I am just joining the chain to the next node. So I ended up having a skew tree. So if I do a find 2 operation, right, I have to call the function 3 times, 4 times, okay? So it consumes time. We can do better. What we can do is, first let's write the problem here. Tree is skewed, okay? And the find function time complexity is increasing. So that's why we use a concept called union by rank. Let's see. Rank is nothing, you can say similar to height, okay? And what the rule says is union the smaller rank set to the bigger rank set. So if I do union 0, 1, because 0 and 1 are at the same level, so we can just do randomly, and we can increase the rank of 0 as 1. Now if you see, if we unite 2, then we have to join 2 to the 0 node. Similarly 3 to the 0 node, okay, because they are having lower ranks than rank of 0. At last, if you do union 1 and 6, then 1's parent is 0 and 6 is having a rank 0 and 0 is having a rank 1, so we'll join 6 to 1. Now if you do find operation like find 3, find 2, find 5, it's just order of 1, right? It's way faster than the previous approach where we don't have any rule how to do the union. So let's see the code for this. In our simple DSU code, we will change few things. We will initialize a rank vector, okay? Initialize all the rank of all the nodes as 0 first. Now let's write our union. First thing, get the parent, ultimate parents of x and y node and check if px equals to py, then we will return, we will not do union. Or else if we will check the rank of the, if rank of parent of x is less than rank of parent of y, then we will join the lesser rank parent to the higher rank parent, parent of px equals to py, and vice versa in the else if, okay? Or else if the rank of px and py are same, then we can choose any one of them as parent and we will increase the rank of the parent, okay? So see, if we have 2 nodes having same rank, and after that we will increase the rank of one of the nodes, okay? So that's it guys, that is what DSU with rank, okay? Union find using rank and with path compression optimizations. So let's revise what we have done at the end. In our DSU class, we initialized parent and rank, okay? Parent, every node is parent of itself and rank as 0 initially. Then we wrote our find function with path compression. Then in union function, we will check the rank of the ultimate parents of the both sets, and we will join the smaller rank set to the bigger rank set. Okay, so that's it. That is all from my side, guys. We will do some good questions on DSU in later videos. If you have any questions, please mention them into the comment box. You will find the problem and the solution links into the description box. If you don't understand, don't like, don't subscribe, but if you do, please show some support. Keep smiling, keep practicing. Thank you.